Now we continue with a graphical study of the equation that we have already established. So the equation given by Albert Einstein is kinetic energy maximum of an electron equals energy of gamma of the photon minus W0. If we replace E gamma by h nu, we get this equation. Now, if we trace a graph showing the kinetic energy as function of frequency, thus the ordinate y is Ke, while the abscissa x is frequency. We compare this equation to what we know in mathematics. We get y equals h or m times x minus W0 is plus b. So this is nothing but the equation of a straight line. And the graph shows a straight line as well. Now we have three different graphs, corresponding to three different metals. The lines are parallel. We're going to talk about this in a second. Now, if we analyze the equation of the straight line, y equal mx plus b, and you compare it to Ke equals h nu minus W0, we notice that the slope m is nothing but h, and minus W0 is nothing but b, or what we know as the y-intercept. So the slope m is the Planck constant h, and the y-intercept is minus W0. So it is okay, it is expected to notice that the three graphs are going to be three parallel straight lines because they have the same slope. And the point of intersection with the y-axis corresponds to negative of the work function of each metal. Now it's important to talk about these dotted lines. Why do we extend the lines as dotted? Because kinetic energy cannot be negative. So physically speaking, we can't have Ke negative. Mathematically speaking, this is a straight line which can extend to infinity. So to respect the physical idea in this mathematical equation, I just added this as dotted line. Not only that, if we consider the x-intercept, the point of intersection with the kinetic energy, is the frequency corresponding to energy h nu equals W0, which is nothing but the threshold frequency. From here, if we go to the graphs, we notice nu S1, nu S2, nu S3 corresponding each to the threshold frequency corresponding to each metal. And here we have a statement referring to this. The x-intercept corresponds to the frequency when kinetic energy is 0. Thus, the x-intercept is the threshold frequency. Now, how can these graphs be obtained? I'm going to move to the simulation that we have seen before and show you that briefly. We will not take a lot of time. So if you observe this graph, you notice that we have the light source. I'm going to increase the intensity so that we'll start having emission. You notice that electrons start leaving the plate. Now, over here I've chosen sodium. I will change the wavelength, thus I'll be changing the frequency. Yes? Now, how can I record the kinetic energy of electrons? In this simulation, there is this graph, electron energy versus light frequency. When I press on it, you will see that graph. Changing the wavelength, notice that this dot changes position because frequency changes and kinetic energy as well. So I'll move from infrared to ultraviolet and back so you can see the line. Okay? There is a nice option here in which I can take a snap of that picture, of that graph. I'll move it to this part here where the region is going to be recorded as a video. Now, changing the metal, if I choose, let's say, copper, and I'll do the same thing. Another snap, moving this here. This is the second graph. Changing one last time to calcium, for example, and then changing the frequency here. Okay, and notice that this is in path, so moving this, I notice that it barely changes here. Okay, again taking a snap, and here it is. You notice we obtained three different graphs, but what's remarkable is that these graphs are parallel. So this is how we can generate these graphs that you have seen. Over here we have a simulation. Later on in universities, you might produce the experiment by yourselves and measure the kinetic energy maximum by using this battery. We're not gonna go there, it's just for extra information. Now we move to a new section, Quantitative Analysis. This is just an analysis of the photoelectric effect once it is obtained, okay? So we are not studying now whether it's gonna happen or not. We admit that the photoelectric effect occurs and takes place. How much electrons will be emitted? Because you know that electrons are related to electric current. Then later on, how much current is produced? By this we will reach the point that I asked you at the beginning. Our main target is to study how is electricity studied and generated using the photoelectric effect. So in order to do the quantitative analysis, once again we have some more equations to deal with. Bear with me a bit. When we finish all these, we're gonna summarize them in one sheet, and you can have that paper with you whenever you have a test or a question to solve. Okay? So first we start by the idea of a source of monochromatic light with a luminous power P emits photons, each of energy E photon equals h nu. We stop here a bit to talk about each term. Monochromatic meaning one color, right? With a luminous power. Power is energy per time. You remember that, right? Power is the energy per time. So this light source, which is a lamp or a lamp like this one, okay, produces photons or produces light. Now, using the photoelectric assumption given by Planck and Einstein, we assume that this light isn't a stream of continuous wave. No, it is a stream of particles which are called photons. You remember that, right? So when you calculate the energy of this source, the energy that it liberates, you can study it using two equations. You can either say it's the power times time, which we know since grade 8 or 9, I guess. And we can also say that it equals the energy of one photon multiplied by the number of emitted photons. So this is an important equation. From this equation, knowing the power of the lamp or the source of light, I can assume or I can calculate the number of emitted photons. Don't expect this number to be low. Expect it to be a number more than 10 to the power 15 or 10 to the power 16 photons. These are very minute small particles you are talking about, right? Now, an assumption that we should always take into consideration as well, the light source here is usually assumed as a point source, not as an object with dimensions. The medium where light propagates is assumed homogeneous, so that when light moves to the left side, it moves to the right side with the same speed and with the same amount. It moves down also and up. It moves in all directions equally with the same probability. The medium is also assumed non-absorbing. So if the power given by the lamp is 1 watt, the power received here is gonna also be 1 watt. So when the lamp produces 1 watt, we assume that this 1 watt is conserved forever, even though in reality it's not, right? So the sentence here, the note continues, unless otherwise indicated. If the problem suggests that energy is lost, that will be clarified. You don't have to worry about it. Now, when a source is far from the plate where photoelectric effect is studied, what happens? Imagine this figure. This is the source, which is the lamp or the study lamp that we have here. The source emits light in all directions. At a certain point, let's say the plate is placed here. Let's suppose that this distance here is d. Okay? So light moves in all directions equally. In all directions, that means on a sphere. So a virtual spherical surface of radius d all around the source. Okay? The plate is a portion of that surface. Make sense? So light is emitted from the source in all directions evenly or equally. Luminous power is conserved. So the power of the source is received by all this virtual sphere. Now, luminous intensity is defined as the power per unit of area. So we divide the power of the source by the overall surface of that sphere to get the luminous intensity. That luminous intensity doesn't change all over the sphere because it is homogeneous. The medium is homogeneous, right? So each portion of the sphere takes evenly the same amount of intensity. From that, intensity I, let's write it here, I, luminous, I'll add it IL so that we won't confuse IL with current later, equals the power received by this plate divided by the surface of this plate. So we use this here, okay, to link the power of the source to the power received by the plate. So if the source is emitting here 1 watt of power, of luminous power, the whole sphere here receives 1 watt. But this plate receives a small fraction of that 1 watt. To find out how much is that, we can use simple ratios, or we can use this equation. Okay? It is a bit hard. When we go to solve a problem, we'll talk about this in more details. Okay? Here is an application about this. Let's read it together. I would suggest that you try to solve it because it's direct. A radio emitter transmits a power of 1 kilowatt at a frequency of 100 megahertz each photon, right? Calculate the energy of 1 photon of the emitted wave or light. The interaction of 1 photon with matter needs few electron volt. Do radio waves interact with matter? You will answer that once you calculate. Calculate the number of photons emitted in each second. So now we have reached the last part of this chapter, the current due to photoelectric effect. Suppose that you have some light here reaching a metallic plate and electrons are emitted. So we admit here that photoelectric effect takes place. We're not studying whether it happens or not. When electrons leave this plate, some of them will be captured by this anode, by this plate here. Any electron leaving this plate and captured by the other produces a positive charge here and negative charge here. Now this negative charge here will produce some flow of electrons in this sense. Therefore, current I will flow in the circuit. The photon causing such an emission is referred to as effective photon. So not all photons are gonna produce electrons or electrons that will be captured by the other plate. The ones that produce electrons reaching the other plate and captured by it are referred to as effective photons. Now, going to calculation of current I is Q over T, and you know that Q equals number of electrons multiplied by the electric charge unit. Number of electrons times E. Now, I have written here N effective, because don't forget that each effective photon liberates or extracts 1 electron. Therefore, the number of effective photons can be detected from the number of electrons reached by the other plate, and that can be calculated or studied using the current. So now you have like a full cycle of studying. Current I thus becomes N of electrons or N of effective photons multiplied by the electric charge unit divided by delta T. Using this, and I'll move 2 slides up, and using this equation, we can have like a quick understanding or an overview about how many photons were emitted by the source, how many photons were reaching the plate, and how many photons were effectively extracting electrons. So these ideas should be with you whenever you solve an exercise. You don't need to memorize a lot of equations. Nevertheless, you know that you're gonna have like a cheat sheet at the end of this session. Over here we can see application 6, which is an exercise involving mostly all the ideas that we have covered. We will solve this next period. So in the upcoming session, we're gonna just focus on solving exercises, and this will be one of them. Till then, I would like you please to try and solve it. No matter how many mistakes you do, the important part is to try your best. Coming to the finale of this chapter, what for did we study photoelectric effect? Basically, right now I can think about 2 ideas. First, in your daily use, you can use photocells, such as in calculators or satellites. These satellites capture sunlight to produce some energy, some electric energy, and store so that they can use later. Another more important application is in physics itself, in a branch called quantum physics. Because after the photoelectric effect, our perspective concerning matter wasn't the same at all. when Albert Einstein suggested that light might have two natures, particle and wave, a dual nature. After a couple of years, another scientist called de Broglie suggested that all matter is like that. Now, after Einstein, de Broglie, and many other scientists, a new branch of physics emerged, and that was the quantum mechanics or quantum physics, in which everything was studied starting from the point of view that matter is somehow a particle and somehow a wave. If you're interested, you can read about that a lot. However, I just wanted to introduce this idea as a consequence of studying the photoelectric effect. Now, moving to the cheat sheet, which you can find attached in Google Classroom as well, you have the basic points of this chapter. Here we have all qualitative study. Quantitative studies start here when you calculate the work function, when you use the kinetic energy max equation or Einstein's equation for photoelectric effect. Then from 9 to 11, these are a bit complicated, but I don't want you to memorize them. You can use them whenever you want. One more thing. I've established this paper or this like summary about what our knowledge about the photon. So according to Einstein, light is made up of particular particles, which are the photons, sharing some weird properties of particles and waves simultaneously. So they are waves and they are particles at the same time. Now, these are the properties. Notice these two important ones, which we have talked about before. A photon interacts with matter according to the rule of all or none. So it's either completely absorbed or nothing. We do not have partial interaction. That's all for today. For next time, please try to review what you have done. Try to solve the applications that we did. And until then, stay safe.